lesson in Chinese, I think my session would be less brain intensive. So, my name is Christoph Schnidrig. I work for NetApp. I manage the system engineering in Switzerland. And I attended the first user group meeting, and we saw a couple of use cases. And I thought it might be interesting for you to present our own use case, which is quite interesting, I believe. So we sell obviously storage systems to the world, and those storage systems are sending back information to us. Mainly to tell us there is a broken disk or a broken fan or whatever. We call that functionality auto-support. So whenever something goes wrong in a storage system, it sends a message back to us. It consists of a couple of log files, XML files, actually CLI command outputs, and things like counter manager, which is really performance counters of the storage systems. We have a huge infrastructure to collect that kind of information. So that's really all the infrastructure. So you see here our customers with the storage systems. IBM is OEMing our systems, so we have the systems from IBM sending us back the information too. So the systems are using either email, so SMTP, or HTTPS to post the messages. One message is between 1 and 10 megs. So we have a number of gateways that receive that information, and from there we have a parser that creates text files. So we have a text file archive with all the messages, and the gateways also trigger a so-called case generation engine. So that means, for instance, when a storage system is telling us, oh, there is a disk broken, we need to detect very quickly that there is a problem. So we will create a case with our support department, and from there, automatically a disk shipment would be initiated. So to give you a couple of numbers, we receive around 3 million auto-support messages a month. So this results in about 1 million messages parsed here, and from there we generate about 90,000 support cases a month. The majority of these support cases are automatically resolved by initiating automatic disk shipments, for instance, or to send back information to the customer, basically telling him how he can resolve the issue. So there is a huge infrastructure behind it. So we have tons of systems that parse that flat file archive in order to, we have a data warehouse. About 5% of the data is injected into that data warehouse, and from there we give basically the customer information back on their systems. They can look into their log files on a web page. We have other parsers that, for example, we have I don't know how many hundreds of internal tools that take advantage of that information. And those tools are using a REST interface to get the information. As an instance, I can do an installed base analysis for Switzerland, so in order to find systems that using a particular configuration and so on. So we had an issue. So the issue was, well, as I said, we have about 600,000 ASIC messages coming in over every week. About 40% is on weekends, so every storage controller is sending back his configuration every weekend. and we had about 2 terabyte growth over the week. So this data needs to be parsed within 15 minutes in order to decide if we should create a support case or not. Which is then, so 5% of the data is going to the data warehouse in order to do further analysis on it. So we were struggling on this data warehouse in terms of performance, in terms of backup, and so on. And we had about 95% of the data sitting around, and we didn't take advantage of it. And yeah, we obviously have many internal departments who would like to get information back, analysis back from those data. And there is obviously a huge untapped potential in this data. So, and the data doubles about every 16 months. So that's because of the growing installed base. So that led us to a Hadoop project. So we had an external company who consulted us, and surprise, the infrastructure is quite similar as pointed out in the first speech. So we used the popular Hadoop functionalities. So basically ASUPs are coming in here. We use Flum to ingest the data into on HDFS. We use Solr to do search on the data, especially when you use the REST interface to request data out of it. Here we have the job scheduler to run map and reuse jobs. And the whole point was to do predictive analysis on the data we are receiving from our customers. So we are using, today we are able to search for known patterns. For example, when a customer produces a configuration issue on the storage, we are able to detect that in advance in order to notify the customer that he should do some corrective measurements on his controllers, in order to make sure, for example, cluster failovers are working properly in case of a hardware error. We use a couple of client apps to access the data, to just give you an idea how this looks like in front of our customers. They have a web interface where they see their installed base, so their storage controllers. So as an instance, NetApp University has 49 storage controllers, and you see kind of a dashboard here. You see we detect 21 risks on those controllers. So you can now click on the risks and you will find recommendations, what they should do in order to make sure that the storage system will run smoothly. So this is one way to access the data produced by a Hadoop framework. Another one is an iPhone app. So a customer can use that app in order to find his risks of the controller, and you see a couple of examples here. So outdated firmware, exposure to a certain box, or things like that are fed back to the customer in order to do a countermeasure on the system before actually something happens. So I think it's a really cool use case for using Hadoop. And how the actual infrastructure, so the physical infrastructure look like is we have a 12-node cluster, so 12 cores in each, 48 gigs of RAM. We use actually a storage system below 4 data nodes. So we use that controller here. So as a storage company and the hype around Hadoop, we have to think where can we add value? And we think we can add value by using here a cheap and deep storage system that is having some RAID in it. So in order when one name node is losing a disk, the whole thing really slows down. So because you have 3 copies of the data as a default in your Hadoop framework, so and the data would be rebalanced in the backend if one of the copy goes away, and this takes time. So per default, it runs at 1 megabyte per second. It can be tuned though, and so we think we can add value here, that we can give you a very fast system with RAID protection, and then you can go down to do 2 data copy in your Hadoop, so to save a little bit of storage there. For the metadata, the single point of failure of a Hadoop is really the metadata of the HDFS. So what we do here is we use one of our low-end storage controller with double RAID protection, and we really use NFS in order to save the metadata of the HDFS on this system. So if one of your name node is going bad, you can easily rebuild the name node with that data. So that's an overall infrastructure solution used actually at our own Hadoop. So I have some performance numbers. So you see we have ingest rate of about 1,000. ASUS is ATO support, so that's really the whole data we get from a single storage system. Or we get about 1.5 gigabytes per minute, so that's not that high. We are able, with that configuration, to parse and load about 1,000 of these ASICs as well. The EMS messages are really you can think of it as an enhanced syslog. So we are able to process 2 billion records within 1 hour. And the ad hoc analysis is really triggered by end users. So if a customer is using the web interface, then we trigger this ad hoc analysis. You see we are quite fast here. So the data is compressed in order to save space and in order to speed it up. So we have to read less from this. New possibilities. So I talked about existing possibilities. We were able to do that in the data warehouse as well. So new possibilities we are using today is we're using the Hadoop framework in order to detect issues. For instance, we are not producing disk drives. So we are using disk drives from the vendors out there. So we are using the information we get back from the customer to analyze if there is an issue with one specific disk drive or one specific firmware in the disk drive. So before that was not possible. So the query ran for 4 weeks. So with Hadoop, we broke it down to 10.5 hours. We're talking about 24 billion records here to parse. And with that, we are able to detect if we introduce, for instance, a new disk drive in our systems, and we're starting to get the information back from the field. We are able to do analysis with Hadoop to see, oh, there might be an issue on that firmware, on that disk, and we can talk to the disk vendor before actually something happens at the customer. Something similar we do is bug detection. So when something goes wrong on the controllers, and not wrong in the sense that the storage system is down, but for example, if there is a performance issue or something like that, we use that data to detect potential bugs in the code. So that helps us to look into code before actually a customer hits the problem. And you see, we have even more records here, so it was way too large to run it from in the data warehouse. So today one run lasts 18 hours. A challenge we still have is the data growth. So you see we basically double the information every 16 months. We have tremendous cost on the ecosystem to run this. And yeah, we could run the Hadoop environment easily for five other years, and it would scale like that. But after that, we would run into significant infrastructure cost and potentially also in a bottleneck. So the beauty of this environment is we can control the client. So we are, with every new release of the operating system of the storage controller, we are looking into it to make it smarter. So in order to just have the information we really need. So at the first step we adjusted the operating system in a sense that it would send the data every day but less data, so that gives us more time in the back end. And we will also adjust it in a way that the storage system would ask first what it should send, what kind of data it should send, and then it would send only the requested data. And by doing that, we think we can reduce the amount of data dramatically. So a couple of references, and that's pretty much it. So, do you have questions?
I would have two questions. One that I would talk to you later about, and one right now. Can you maybe go to the slide where you showed the hardware architecture, particularly where you use the NetApp for storage?
That one?
Yeah, I think so. You were talking specifically about the cost of the system, and actually this slide triggered that question for me already. One of the compelling use cases for Hadoop is that you can use commodity hardware. Because if you're adding a new data node, you're not only adding new storage, you're also adding more computation power. So one question I would have is, how expensive is it to use NetApp storage arrays for doing that? And not only in terms of cost, but also, are you using data locality because of that? So when I saw your performance number for 200 megabytes per second with compressed data, that sounded very, very low to me.
Well, that's obviously not the limit of the backend system. That's more the limit of the node. So we think we are talking about an enterprise usage of the Hadoop framework here. So that really means I cannot afford that the whole system slows down. And so for that purpose, we think it is, I must say that's not a traditional NetApp array. So that's a cheap and deep box. That's a traditional NetApp system, and that's a low-end controller. So the costs are compared to enterprise storage solutions is quite low here. So as I mentioned, we want to make sure that if one node is losing a disk drive and you have all this rebalance stuff going on in the background, then you not only saturate the network here and keeping the nodes busy doing the rebalance. I think a 3 terabyte SATA drive, if you lose one drive, it lasts 72 hours to rebalance in the backend. So that would mean 72 hours reduced performance in the whole infrastructure. And here, we can't really afford that. So what we're doing, we are kind of balancing the cost and availability or the performance of the whole system. So, as I said, we're using cheaper deep arrays here, usually based on SATA disks. We are using a RAID system here. So if one disk is going bad, the storage system will do the rebuild. So it would be fully transparent to the Hadoop. which is not when you're using commodity hardware in the servers and you're using a disk drive. So that's the whole thinking behind this design. And on the other hand, if you would lose the HDFS metadata, basically you can wipe out the whole thing rather than start from scratch. So what we're trying to do here is we're using a storage controller that has that can use snapshots in order to do backup on remote systems. For instance, you're using rate protection here. So this guy is really here to protect your metadata, so to remove the single point of failure of the Hadoop metadata. I agree with you that when you build up a system where you can easily reproduce the data, or you potentially have much less data linked, then it makes potentially more sense to use commodity hardware. So at the end of the day, we're using commodity hardware here as well, but with a sophisticated storage operating system.
So I mean, I don't want to argue about the preferences that you pick, because I think this is really depends on the use case. So you could, for instance, I think the trade-off, we put more money, more investment in the storage area, so that we can get better performance out of the network, which I think is the main reason. You said rebalancing might cause a delay in the network.
And out of the nodes as well, in case of failure.
Okay.
So, I mean, that is pretty much going back of the start of the whole enterprise storage, right? In the beginning you had disk drive and your servers, and then the whole storage, enterprise storage began to arise in order to solve the problem you had on the servers, in order to mirror the data, in order to make it more reliable, and that's kind of a balance here as well, right?
We can talk later. Sure. And thanks for your talk. Very nice.
One question. You mentioned that the data that you receive from your clients is more or less unstructured, text log based
Yes.
data. And how do you make this data processable? Means is there some kind of text analysis also behind that?
Yes. So on one hand, we try to get away from unstructured data from the controllers. So yes, we have log files, but we try to make them more structured. So that's the whole EMS system. Probably not in here. Yeah, that's a problem today, that we have to parse a lot of information. So I must admit, I talked actually to the guys who implemented it, but I'm afraid I can't answer your question.
But it's a self-implementation, I guess. MapReduce also, or what are you using?
Yes.
Mm-hmm.
Yeah. Here.
Yeah.
I guess we parse it inside the framework.
Okay. Thank you.
Thanks a lot.